All right, we'll go ahead and get started here. Thanks everyone for joining this webinar this morning. My name is Dave Lewis. I'm an engineer here at Bentley Systems, and today on this webinar we're going to talk about transfer voltages and analyzing touch voltages outside the substation. Do appreciate everybody calling in this morning or this afternoon, depending on your location. The purpose of this webinar today is really to discuss hazardous transfer voltages and how engineers are going to evaluate them. And it's my goal at the end of this webinar that you'll be able to define transfer voltages, identify scenarios that could be transfer voltage hazards, and analyze and design mitigation with XGS Lab. Um, Before we get started into this actual webinar, I do want to launch a couple polls to get an understanding of where our audience's knowledge is at. So let's go ahead and launch our first poll here. Do appreciate if you can take a moment to answer the poll. Question is, how familiar are you with the IEEE Standard 80 Guide for Safety in AC Substation Grounding? I think we have most people responding and appreciate your voting. And as you can see, definitely appreciate everybody's responses. And most of the audience is familiar with the terms. There's about equal spread of people that are new to the subject and people that are referencing IEEE 80 on a regular basis. It's important to note we will be going over some of the basics of a grounding analysis, which is the purpose of the IEEE Standard 80 Guide, to give everybody an equal playing field as we go a little bit deeper and talk about transfer voltage analyses. I have one more poll specific to transfer voltages. How familiar are you with transfer voltage studies? And this will be interesting just to understand if people are currently performing these studies. I think most people are going to be familiar with the concepts and most likely not a significant number actually performing them on a regular basis, just based off of typical industry practices. All right, and as we can see, kind of as expected, not very many of us are actually performing these transfer voltage studies very frequently. Most of us are familiar with the concepts, and there's a large percentage that are just looking to learn through this webinar, and definitely appreciate everybody calling into this. We do want this to be a fun experience. So with that, let's go ahead and jump into our webinar this morning and make sure we can kind of get all of these things covered. In this webinar this morning, we're really going to talk about the basics of grounding to start off, make sure everyone understands the preliminary concerns or the initial concerns related to grounding studies before we jump into talking about transfer voltages and defining those. We'll highlight some examples of a transfer voltage hazard, and most of our time in this webinar we're going to spend actually using the software to evaluate different case studies, looking at different mitigation strategies and how to apply them as an engineer might when they're coming up with their design practices. Of course, when you have these types of studies, all the information that you can get is very valuable. Soil resistivity data, fault information, actual measurements, if you can, of any transfer voltages is very valuable so that you can bring that into your analysis world and develop designs more accurately. So with that, let's go ahead and jump into some of the basics of grounding system analysis. So for those of you that are not familiar, grounding systems are common for substations, switchyards, generation sites, and some industrial facilities. And these are essentially buried conductor into the earth. And you can see on the right, we have a trench that they're placing bare copper into the earth. And then they're just going to backfill that. And that's going to be the basis of our grounding system. And when a completed system is installed, it'll look like our illustration on the left, where we have a substation where our highlighted lines represent our ground grid, and it makes this mesh pattern. And that mesh provides a couple things. One, it makes for a short distance to run our ground bond from our equipment to our ground grid, but it also helps to reduce voltage differences in the soil. And what I mean by that is when we have a power system fault, a single line of ground fault current will go through the earth, and that can produce what's referred to as the ground potential rise. And on the right, the ground potential rise is somewhat illustrated. This is actually the Earth's surface potential, and this represents the potential that we have relative to some remote point or a point that has no potential. And that mesh that we see in our illustration here serves to make something of a plateau. So what we're trying to do with our grounding systems is to reduce voltage difference between our grounded bonded equipment and the Earth's surface that an individual may be standing on. And the reason that we're putting all this material into the Earth, and just make sure I have the question bar open. The reason we're putting all this material into the Earth is so that we can help promote personnel and public safety. And the IEEE Standard 80, if you read through that, it provides a lot of beneficial information. Number one value that it provides is that it gives you criteria for the touch and step voltage limits. It also gives the hand-to-hand voltage limits as well, but primarily when we're doing a grounding system analysis for a substation application or generation site, we're primarily looking at these touch voltages or step voltages. And those of you that are not familiar, a touch voltage is essentially when you have your hand in contact with a piece of equipment, and during that fault, that experiences the GPR, the ground potential rise of 1,000 volts. The soil may be at a different potential of 800 volts, and so the difference between those is 200 volts, so that would be a 200 volt touch voltage. On the right, we have an illustration of an individual, same fault condition, but they are not making contact with any grounded or bonded piece of equipment. They're just simply walking across the yard. And simply by the span of 1 foot to another on the Earth's surface, they can have a voltage difference on their feet, and that could be 900 minus 800, which is a 100 volt step voltage. And so these are the primary concerns that we're looking at for a grounding system analysis. And typical industry practice is going to be looking at your substation and within contact of that substation fence, like the swing of the gate included in that. So now the question becomes, what is a transfer voltage and why are we on this webinar this morning? Well, transfer voltage is really a touch voltage scenario that is transferred into or transferred out from a station to some other entity. Typically, we're looking at another metallic object, and you could have transfer voltages through direct metallic conduction, meaning your recipient of this transferred voltage may be directly bonded to your grounding system of your substation or other grounding system. You could also have conduction through the soil, and you don't need to have any sort of direct bond. It's just by being in the vicinity, the current will go through all paths available to it. So you have this conduction through the soil. And an illustration of this would be on the inside of our substation, as you can kind of see the supports for the barbed wire for our substation fence. This would be a typical touch voltage analysis. We look at a step voltage analysis, a touch voltage, but this individual touching this fence that it may be directly ran to this substation fence, this can be considered a transferred voltage. If this is directly metallically connected to the substation fence, that's likely to have an equivalent voltage to the GPR or similar to that voltage. And so this individual in contact with that, their hand will be at a significantly higher voltage than what their feet will be at. So this is really the area of concern that we're looking at in this webinar when we talk about transfer voltages. And just to give some real world examples of what this might look like, here we have an example of a substation fence. You can see that on the right. There's a little warning sign of a shock hazard. This is the substation fence. And if you're able to see this, there's an air gap between the substation fence post and this fence post here. The purpose of that little air gap is really to provide a non-direct metallic, avoiding that direct metallic connection from the perimeter fence of this facility to the grounding system. However, even though this appears isolated, on closer inspection, you can actually see there's a little ground lead coming up and making contact with the far side of this support post. And that, of course, is going to be providing a direct metallic connection or direct metallic conduction of transfer voltages to this perimeter fence of whatever this facility may be. So this is a good example of an engineer may have been aware of the issue and provided an engineered design to mitigate for transfer voltages, and that may have been observed as being a mistake because of lack of knowledge about transfer voltages. Typically, substations were trying to ground and bond everything, so we know the voltage, transfer voltages. It may be best to ground and bond it, or it may be best to try to insulate and isolate. Another example can be a substation to substation. Because of different fault currents, grounding system layout, protective clearing, we can have different voltage values or ground potential rise that can transfer from one substation to another, either through shield wires or through that metallic conduction or the soil conduction that we talked about. And a pretty common one, again, is pipes. Pipes are in the ground in many of our urban environments or our rural environments, and it's often convenient to run pipelines in the same right of way as our transmission lines. Because of that, we can also have issues where we have transfer voltages from our station to adjacent pipelines. And another thing about pipelines is that they're often having a protective coating on them that is to insulate them from the soil. If you can transfer enough voltage onto that pipe, that protective coating can carry that voltage a very long distance out, so far out that you can carry a significant voltage on the pipeline out to an area where your soil voltage is close to zero. So that can be an issue where your pipeline that can be a mile or two out from the substation could still be a touch voltage hazard or transfer voltage hazard. And another example is just a substation next to a facility. Here we could have personnel safety hazards, meaning any metallic objects within this facility could be energized during a fault due to that transfer voltages. And we can also cause damage to the equipment within that facility, especially if it has sensitive manufacturing equipment. So all of these things for transfer voltages we want to try to avoid. And by simply being aware of it through this webinar and other discussions, we can start taking steps to identify these hazards and start mitigating those. So with that, we're going to switch gears here and open up XGS Lab and start jumping into some case studies. So the first case study that we want to look at, if you've attended some of our workshops, we do have a grounding workshop on a quarterly basis. This is our typical substation that we do an analysis for. And outside of that substation, we are representing a floating tank. It could be water storage or some sort of gas storage. But if we rotate my view here, you can see this tank is embedded into the earth, and we can have conduction through the earth to that metallic structure. So if I go to XGS Lab, here we have the start page, and I've already created the model or created the project. So I'm just going to select GSAFD, and I will set my reference standards, and we're just going to get this project established for our example here. We need to, just like with the normal substation analysis, create our soil model, which is going to be derived typically from soil resistivity information. If you need more information on that, highly recommend reviewing the IEEE Standard 81. That's kind of the sister guide of IEEE Standard 80. It provides all the measurement techniques for related to grounding systems. So here is, I've just clicked on to the SRA tool within XGS Lab, and this is going to interpret native soil resistivity measurements into a soil model. And I'm just going to take one set of traverses. Usually you'll have multiple sets of data. Just for our webinar this morning, we'll keep it simple. So here, pasting that in, we see a little preview window of those resistivity measurements, and I'm going to use the automatic detection to create my 3-layer soil model represented here. In our substation, we may need to account for any surfacing layer like the crushed rock. Do note that 3000 ohm meter may or may not be applicable for your actual scenario, but we'll be able to turn that on and off as we get into the touch and step voltage criteria. So here we have our soil model plot. Next, we need to pull in our grounding system, energize that, and see how much voltage is transferred to our external tank. And what we're really concerned about is touch voltages of something on this transferring from our substation. So we'll just set the scale of our drawing and pull in the drawing as we normally would for a XGSAB analysis. And I'll go to my DXF file here, pull in my ground grid, assign the proper electrode for this. And I do need to shift this into the earth for my analysis because typically if you're getting this drawings from a CAD package, part of these transfer voltages analyses is bringing in information from different resources. So combining those into CAD is relatively convenient for being able to do a study with XGS. Next thing I want to do is create my ground rods in this model so we can see those, the effect of those. So now we have my grounding system layout. I need to pull in that yellow conductor, which is the E-tank layer. And I will give that electrode 1 definition and assign some conductor to that. We'll just use this generic conductor for it and import this. So once we have the conductors imported into this model, we have a nice little list of all the conductors, and I go to my draw view and we can see here is that tank floating out in our soil, and this is our grounding system, and we're concerned about how much current is going to transfer through this system, and are we going to have a touch voltage hazard. So we'll assign a fault current, and this is something you typically get from your short circuit software. And just as a hypothetical, we'll put 5 kA as fault current. That would represent your single line to ground fault. I will set my touch voltage criteria. And these are just based off of IEEE's 80 calculation methodologies. And we'll do debug and compute. And what this is doing now is actually calculating the ground potential rise based off of the grid resistance or the impedance that's calculated from the software. And we will take a look at the potential of our grounding system and the potential of this tank that has just had conduction through the soil. And we are going to do this case example. We're also going to look at transfer voltages to a fence line, perimeter fence line. And if we have time, I'll look into a transfer voltage to from a substation to a pipeline, particularly looking at appurtenances or test valves coming off of that pipeline. So we do have 3 different case studies that we intend to walk through with this morning. So this analysis is completed. We can see at the high level our grid resistance is about 2 ohms with 5,000 amps going through that grid. We end up with a 10 kV ground potential rise. If we look at the voltage of our grounding system, what we will see, I'll get rid of the tank for this plot. You see there's a little gradient in the voltage of this system because for transfer voltage studies, you really want to use GSA or GSA-FD or XGSA-FD. Both of these modules account for the self-impedance and mutual impedance of every little piece of conductor. You do need to account for that voltage drop because as you are, especially with fence examples, you'll have voltage drops as you go across the Earth's surface on these recipient structures that need to be accounted for. Let's go ahead and now we can see our voltage or ground potential rise of our station. We want to see the voltage that's actually transferred to the tank. We'll see this tank is approximately 4,000 volts that's been elevated because of the conduction through the soil. It doesn't have any direct metallic conduction. Now let's go ahead and look at the area calculation of this. So here we'll actually calculate the Earth's surface potential. So all of these little red dots is the resolution that we are using as we calculate the Earth's surface potentials. Since we have the metallic portion already calculated, now we are going to calculate the Earth's surface potential. And that's going to tell us, we know that where your hand will be in contact with, we need to know what your feet are in contact with, and then we can do the touch voltage of those. So traditionally, when you do a analysis for a substation, you'll set your reference for your touch and step voltages to your fault point, as that would be your highest GPR. And we can produce a simple little plot here. Green means you're compliant to touch and step voltages, yellow means you're exceeding touch voltages, and red means you're exceeding touch and step voltage criteria. We put on some surfacing layer, and we'll see here, with surfacing at a substation, we would anticipate we are meeting compliance criteria within this area, but a lot of the station needs some mitigation for it. Note that regardless, our tank was not passing for a surfaced or non-surfaced condition. And part of that is because we need to make sure we're specifying our references. So when you're using software like XGS Lab, you can have control about what things an individual will be in contact with. And what we can do is we're going to specify an individual can only be in contact with this tank. And we're going to turn off this surface covering layer so that we use the touch and step voltage criteria without any sort of crushed rock surfacing. With that, I'll modify my reach to be more in the 20 feet reach, and then I'm going to plot my safe areas here. And what we can see is similar, as I guess really much different than what we saw before. Here, we're now seeing a green area, a green band show up around the tank where we are now compliant for touch and step voltages with reference to that tank's voltage. And the reason for this is we already looked at our tank voltage. It's about 4,000 volts. If we plot the Earth's surface potential, this band is about 4,000 volts. So where we are within that compliance criteria, that 200 volt touch voltage difference, that's where we are going to pass for touch and step voltage criteria. As we get closer to the substation, the ground potential rise or the Earth's surface voltage is elevated up to 6,000 volts as you get right at this ground loop. That means that we're going to have several 1,000-volt difference between the voltage of our tank and the Earth's surface, and that's something that we need to mitigate. And one methodology for doing that is let's improve our grounding system performance, for instance. We already know we need to mitigate it. One simple, easy way to do this is let's account for our fault split factor. And for those of you that aren't familiar with this, this is really I actually have a good little slide from the previous workshop we did. I'll pull up. So when we have a fault on our power system, as we are doing here, we can imagine this is where my 5,000 amps of current are going in. In reality, your substation may have shield wires that's interconnected with and distribution neutrals. Those are additional paths for current to go that current won't need to go through your grounding system and produce the touch and step voltages. It can go through these alternative paths and reduce the GPR and reduce the touch and step voltages. And the methodology for accounting for that, there's several different ways. You can do some hand calculations. There is a tables in IEEE 80. This is the Annex C. I will caution the use of this annex because there are many assumptions involved in the calculation methodology, such as transmission line length, the resistance of the tower footings, the type of material that are used for the shield wires or neutrals. Barring that, just for this webinar, we can look in this calculation and see if this station had 2 transmission lines and 4 distribution lines coming from it, a Thevenin equivalent impedance of that network would look like 1 ohm plus J.2. So in XGS Lab, let's go ahead and account for that. So I'll go to my split factor here. We know our grid resistance is approximately 2 ohms. Fault current was approximately 5,000. We have the 60 hertz frequency with the 0.5 second clearing time. X over R, this will account for the decrement factor or that asymmetry in their fault current. And then we'll put in 1.09 and 0.208. Those are the equivalent resistance reactance that we saw from that annex. And then here we can see 1,800 amps is approximately how much current would be expected to go through our grounding system. So with that, let's just scale the results to 36% of the total fault current. So if we go to my analysis, if you're using XGS Lab, you can go to distributions, put in this 0.36 scaling factor, And then we're just going to scale our results by that value. So if we replot the Earth's surface potential, we see this band is no longer 4,000 volts, but more like 1,500. If we replot the touch voltages to the tank, now we see much more green around this band. There may be a little bit of touch voltages right at this corner that we might need to mitigate still, but this would be an illustration of how we would, one methodology for mitigating transfer voltages is by improving our grounding system performance or by sharpening our pencil to do a more accurate grounding system analysis, to therefore do a more accurate transfer voltage analysis. I think key takeaways from this is really making sure that you set your references accurately. So if I switch my reference point back to my substation and I replot that same variance plot, this would give a false indication that we are no longer compliant to IEEE 80's criteria for transfer voltages. That's an important detail that is easily missed if you're not familiar with more advanced tools like GSAFD or XGSAFD. Now with that, let's go ahead and transfer into another case study where we'll look at transfer voltages to a fence line. So I'll go ahead and open up the model of XGSLab. And this is just loading up as we go here. So we're going to look at our fence example. Again, we're starting with a fresh XGSLab model. So here we are going to pull in this CAD model. Not that one, actually. Where is my transfer voltage to the fence line? Here we go. All right, so here we have a substation grounding system illustrated in this light green. And if I rotate my view, you can see here we have a representation of our fence that is illustrated by this little white line with the fence post supporting that fence mesh. And then we have the red conductor, which would be a representation of an external fencing. So here, what we'll do is import these conductors. Let me go back to XGSLab. This time I'm going to use XGSAFD. I'm going to model that fence line above grade, so I want to have that analysis with the above and below calculations. We'll set our reference standards again to IEEE standard 80. We'll set our frequency. And instead of doing a soil calculation, we're just going to put in uniform 200 ohm meter soil. And I will import this model. And I need to set the scale and point to the CAD file, which I will pull from here. Another thing with XGS, if you're using it, you can pull in the layers based off of a previously developed XML file. So here, now I have all the layers associated with that drawing that I want to import. And now we can just go directly to importing the model. Any mitigation, of course, if you make that, you can export back out as the DXF. So we have a list of all of our conductors, going to the draw view. Now we can see here is our perimeter fence line. There's our substation represented in XGSLab. We'll just kind of zoom in at this point and illustrate. There's a little physical metallic connection between our external fence that connects to our substation fence, which may or may not be the best practice, as we'll see in this transfer voltage webinar. If you can, whenever possible, provide some isolation between your substation fence and perimeter fencing or other sort of fencing that goes outside of your station. So let's go ahead and energize this station. We'll use that same 5,000 amp fault current. This time, let's assume that that 5,000 amps is post fault current split calculation. We've already accounted for that so that we are already closer on accuracy on our analysis. We also want to calculate our touch and step voltage criteria for IEEE 80. Let's go ahead and debug and compute. At this point now, the software is highlighting that I forgot to make some connections. So I do want my software to connect insulated conductors, so I will do this. And those insulated conductors, your fence mesh, if you model that below grade, you can insulate them. That way it doesn't have a connection between fence posts to the earth. It's a way to model a fence in GSAFD without having the capabilities of XGSAFD. So with that, we'll hit debug. All right, debug successful, and now we can compute. And with this, now our results have finished. At a high level, we can see 5,000 amps into a 0.8 ohm system will result in approximately 4,000 volts as our ground potential rise. We can see that illustrated when we look at the potential of our system. If I zoom out here, here's my substation in red, and then over on this corner is where we reduce the voltage most significantly, almost to 2,000 volts as we go away from our station. And as you can suspect, we know the voltage on this external fence goes from about 4,000 volts out to 2,000 volts. If our compliance criteria is approximately 215 volts, we can anticipate we're probably going to have some transfer voltage issues here. So let's go ahead and take a look at that by going to our area calculation. I'll just specify the area that I want to do my analysis for. And what we can see, just plotting the Earth's surface potentials, I can see this fence line is actually carrying out some of the, or elevating some of the Earth's surface voltage because it's carrying that 4,000 volts out here. As we go out diagonally from the station, the voltage decreases from 4,000 to about 1,000 volts. With our fence line being about 2,000 volts out here, that's a 1,000 volt difference. So we're definitely going to have touch voltage issues at this site. Again, we'll switch to all elements. I do want to specify what things I'm making contact with again. So I'm just going to look at the external fence and external mesh of that fence and plot my safety plot. And it's a little hard to see, but if I extend this to be a little wider view, this little yellow band is indicative that we are not meeting the touch voltage criteria within reach of this external fence. So we need to develop some mitigation strategies for this. And one methodology for that is if this fence is a perimeter fence for non-essential equipment or something that's not a high security, we could recommend mitigation with a wood or non-conductive fence type. And we can do that strategy simply by going into my model, and I'll zoom in here so you can get a little better view of this. So I'm selecting the fence mesh, and I'm selecting some point where I want to make a disconnection. So if I got a couple fence posts and fence mesh that I'm now going to divide at these intersections. Now I can select all of this conductor, that's my external fence, and disable that. So I'm removing this from the model as if it is no longer a conductive component. It's just something that is in the background of my model. It could represent a plastic fence or a wood fence, something that's non-conductive. We're going to do the same type of operation on this side of our fence line. And I'm just picking a spot that's far enough away from our station based off of the Earth's surface potential that I believe this would allow us to be far enough away from the station that we won't have conduction through the Earth's surface and that result in touch and set voltages. So again, I'm going to disable these conductors. There we go. And with that, I'm just going to hit debug just to make sure this is take rid of the issues as I ran through the modification there. I have one. So in XGSLab, I have both of these systems defined as electrode 1, meaning in the software I'm telling it they should be interconnected. I don't want that to actually be the case. I'm purposely creating some isolation either through some sort of non-conductive fencing. So I'm going to exclude those from that connection checks and rerun my model. And again, this is just to illustrate another way that a user can analyze our transfer voltages onto other recipient objects outside of the station. So here we didn't really affect the, well, I guess we did really kind of affect the GPR. So because we no longer have that direct connection to this external perimeter fence, our grounding system voltage actually elevated to 5,900 volts. So it has a higher impedance. But even though that has that higher impedance, redraw this area. We want to see if we've managed to get far enough away from our substation to reduce transfer voltages to that perimeter fence. I'm gonna have my exclusions here. So I'll plot my safe areas. And we might have a little bit of a touch voltage right at this corner here. That one probably looks a little fine, but green around this perimeter fence, that is a good indication that you are now meeting the touch voltage criteria from IEEE 80 as we're applying that to a transfer voltage scenario. We want to get a little more detailed on this. Let me plot right. I think it was down here that we might have had that transfer voltage still there. So I'm going to do a little closer examination on this corner. Again, setting my reference elements, and I'm going to only look 3 feet outside of that perimeter fence. In here, we can see the maximum touch voltage to this perimeter fence is 187 volts. That is below the touch voltage criteria from IEEE 80, which is 215. So in this case, we've now created a new mitigation strategy and mitigated this model. We'll save that. And this is another strategy that we'd implement as far as mitigation approaches go for XGSLab. I'm going to close this down. I'm going to open up a new model here. And this one, because we're coming up close to the top of the hour, I do want to make sure I get to questions. So we'll simplify this. We won't go through all the process for the pipeline mitigation, but I do want to make sure we walk through how we start designing mitigation for this system. So now we're going to look at mitigating a transfer voltage hazard to a pipeline that's crossing between 2 stations. As you can imagine, there's going to be significant transfer voltage along here, and the parallel section here is about 70 to 100 feet, so a fairly large exposure span. Again, I'll set my reference standards to IEEE 80 because that's what I will use for my touch voltage criteria. I'll set my frequency to 60 Hertz since we're using XGSAFD. And now I want to import this model. This one, I believe, is drafted in centimeters. And we'll go to my CAD model again to pull in this pipeline model. And again, I already have a pre-developed import list, so I'm just going to import all the conductors associated with that pipeline, the pipe itself, and this test pipe will be referred to as an appurtenance. That's going to be like what we saw in our previous sections of the webinar. Here it could be a test valve or some sort of valve that we might have personnel making regular contact with and being regularly exposed to transfer voltage hazards, or the possibility of those. So here we've imported into XGSLab, we have our model, and we're going to look at transfer voltages to the parts of the pipeline that are above grade at each of these little dots. That's our appurtenances. Before we get into that, I do want to make sure we create some infinite lengths at the end of my pipeline. This is an important step for doing these types of models because we don't want to have end effects in my model. Another thing we need to do, obviously, is energize our system. Just like before, let's assume we've already accounted for the fault current split, and we are just going to put in 5,000 amps as our energizing value. We'll specify the touch and set voltage criteria based off of our clearing time in the soil. And now we can go on to, I need to do one thing. Back in my data, I need to make sure that we are allowing insulated conductors to be connected. And the reason we need that is because we have my pipe, which is a pipe type. And in my libraries, if we go to that, we can see here, this pipeline is an insulated conductor. And the same thing with my pipeline's test valve, which is just a 2-inch pipe coming off of that. So both of those are insulated conductors that need to be accounted for as allowing for insulation connections. With that, we should be able to debug and compute. And what we want to see here is that we have compliance issues essentially for this. All right, completed the analysis. So let's go ahead and look at some of the voltage characteristics of this pipeline. So we'll go to potentials. Let's just plot the pipeline voltage here. And viewing 2D, we can see this pipeline has some significant potential of 210 volts that's transferred onto it. Another thing we might look at for pipelines that are in particular is this covering stress voltage, meaning that pipeline coating, the ground potential rise and the earth surface voltage as it's elevated could be significant enough that it can puncture through that insulation. It can exceed the dielectric strength of that. And that could lead to accelerated corrosion, and that could lead to more serious issues as well. So we do want to look out for that for pipelines in particular. So here we have 2000 kV as our covering stress voltage, which may or may not exceed the dielectric strength of that pipe. But let's focus back on to personal safety aspects. And so what I want to look at is way far away, we have this test valve. I'm going to calculate the earth surface potential around that. We already know the pipe's voltage. I'm just going to do my safety plot to that point. We can see green within 4 feet of that appurtenance, meaning we are within the compliance criteria of IEEE 80. But if we look closer to where our substations are, we can expect the earth surface potential here is much greater, up to 1,000 volts. We already know our pipeline is about 200 volts, so if we plot our touch voltage to that object, here what we see is non-compliance. And if we look on the right-hand side on the legend, the maximum touch potential within 3 feet is about 1,000 volts. So obviously not a good result for this. What I will do in this project, just to simplify things, I want to illustrate how you would actually start doing the design, and I'm going to open up a previously mitigated model just for the sake of having this completed in a timely manner. Usually when I do these types of transfer voltage analyses, we'll look into the area of concern, and now we're going to put in some mitigation. And this can be something that's called a gradient control mat. What that looks like in real world is, report here. So this would be an illustration of a gradient control mat. It could be just a dense mesh below some of your pipe equipment. It could be a little disc that goes around that. We're going to reference a little disc that goes around. So we're going to put in some conductor, make this a stranded 4-aught conductor. I'll force this to just be 3 feet surrounding my appurtenance. And then in the X, I snap to that end of that conductor, and now I have a little loop around my appurtenance that I want to protect. And then I'm just going to create a little bit of a mesh so that I can get a better equipotential voltage around this appurtenance. You can see on the XZ view, when I snapped, it actually snapped to the top of that appurtenance or the top of that pipe. Let's go ahead and shift that down. I want that to actually go down to, say, 6 inches. So I'll just manually force that value into the earth. And now we've put in one test station, or one mitigation strategy for one of our test stations. And what we see, if I, just to give a little example of what I want to highlight here, if we reran our analysis before we had a touch voltage hazard at this point closest to our substation, when you introduce mitigation strategies, it changes how your system operates, and it can change things beneficially, ideally, but we can also start to see some hazards introduced by our mitigation approach. So here, let me just draw, area calculation. So if I look at my touch and step voltages to my test pipe, we'll plot the safe areas around that. We start to see green, meaning we're compliant for touch voltages to a certain extent, but now we have this red ring occur. And this is because our Earth's surface potential is around 1,000 volts and our pipeline voltage is around 200 volts. We are introducing a new step voltage hazard with this gradient control mat. And that's something now that we'll have to try to mitigate. And for the sake of time, I wasn't sure if I'd be able to actually develop all of this during our webinar today. So I already have a pre-completed model to represent the full extent of mitigation. And just to highlight this, if we go to the draw view, in order to mitigate that, it needs significantly more conductors. So here we're actually going out approximately 24 feet away from that the test station. And if you look on the XZ view, it actually is making a little bit of a pyramid shape so that we can reduce more gradually the drop off in the Earth's surface, or the drop off in that soil voltage, so that we can make sure to have a more a lower steep in our voltage and reduced step voltages. By putting in all this conductor, we ended up having an issue as we elevated the pipeline voltage with all of that material. So out here, when we were compliant, we now needed to have some mitigation. And we can see that illustrated when I go to my area calculations here. Now I'm going to calculate the Earth's surface potential and the touch and step voltage criteria here. And once I do these plots, just to prove that we've mitigated the system, I'll go to the questions that have been popping up. And I want to look at my test station. So here you can see all green, we are compliant to IEEE's touch and step voltage criteria. Let's zoom out. And this one, that was our trouble spot. Let's go ahead and recalculate the touch and step voltage around this point here. And look at my, all right, making sure I have the right reference. I may have had the wrong model here. We'll just pretend that that's green for this example, so that we can actually say that we're compliant. But really what we should be saying here is green has occurred throughout the site. This might be the non-exactly accurate model. Apologies for that. Anyways, I do need to get to questions here so that we can make sure that people are walking away from this webinar having all their questions answered. So in that regard, let me go ahead and look in our question menu. And thank you everybody for entering questions as we went along. I know we kind of covered a lot of content relatively quickly. Final things I'd want to say about this are, when you're doing a transfer voltage study, you can insulate, isolate, you can add direct grounding or bonding. There's multiple different correct strategies in order to find mitigation. Simplest is adding mitigation to your existing substation and being more precise on your calculation methodology. Others are adding those gradient control mats, non-conductive barriers, and adding other objects into your model, as that can affect the entirety of your system and help reduce those ground potential, help reduce that ground potential and reduce touch and step voltages. What we'll say is you can do many different transfer voltage studies because there's a whole world of recipients out there, and they are approachable as long as you have the correct information and the right tools to do these. You really need a tool like GSAFD or FGSAFD to do these types of analyses accurately. With GSA, it won't account for that voltage drop that we were seeing in our fence line and our pipeline and all these other types of external entities. So with that, I do want to make sure, going to questions now. One of the first questions is, knowing that there is a GPR, well, that GPR is what will produce this transferred voltages. The NESC doesn't provide a threshold for ground potential rise, whereas the Canadian Electric Code does recommend a 5,000 volt ground potential rise. Why is there such a difference in that? Why is there such a difference, and does the GPR matter? What I'll say is the GPR isn't like the most accurate methodology for measuring the success of your grounding system. Really what we are looking at is how well two voltages match each other, meaning the voltage of the Earth's surface and the voltage of the thing that you're going to touch. That said, a higher ground potential rise can allow a higher touch voltage. So the GPR will correlate to the touch voltage and correlate to the transfer voltage hazard, but it isn't a direct indication of how significant hazards may be. So for that reason, there's that disconnect between the two standards. Personally, I think the best methodology is that the standard should indicate that touch voltages and transfer voltages should meet the criteria from IEEE 80, which IEEE 80 accounts for the differences in those voltages between the soil and the recipient, the clearing time that is associated with that, how long somebody will have to withstand that shock, and what the human body's threshold is for that shock. So that would really be the more holistic approach in order to analyze that. Good question. Next question is, how do you choose the item to look for transfer voltages? Is there any zone of influence that we should look at or something else to determine what needs to be checked? Great question. So if I go to my pipeline indication here, what we can do is look at our compliance criteria and say the touch voltages without any sort of surfacing is 200 volts approximately. And then if I go to my analysis and recalculate my Earth's surface potential, which I will do once I zoom out. So we'll view this and do just a really quick calculation of this. Notice I have a very sparse resolution, so we can generate this relatively quickly. So here, this is the Earth's surface potential, and as we go out, eventually we are going to find somewhere along this line, we are at 215 volts, which is essentially our touch voltage, right near the edge of our corner here. Actually, extending past our corner. At a minimum, or I guess at the maximum distance, it's possible to have a touch voltage when your Earth's surface potential is above that touch voltage criteria. Meaning if you had a pipe that was just coming along the edge of this system and a test lead were right here, or a test valve, it's possible that pipeline may be at 0 volts and the individual's feet will be at 260 volts, and so that could be a touch voltage criteria or a transfer voltage hazard. Now this is going out approximately 1,000 feet from our station. It can go farther or it can be less depending on your soil characteristics, your grid resistance, your fault current, your compliance criteria. But that would be one methodology for evaluating the extent that you can have transfer voltages. Another, you can use 2 times your touch voltage criteria. So if that's the case, let's go ahead and set a little contour here. And I'll say, actually I'm gonna set a level, and then we'll put this at 550 volts, plot this, and then we can create this little plot of within this zone, if we have any metallic structures crossing this line, that means we can have transfer voltage into or out of this system. Those types of recipients would be things that we would look into. And then this is a plot that you can actually export out to the DXF, because there are some countries where you need to specify within 1,000 volts, these types of entities need to be evaluated, or 300 volts. This is one methodology that you can do that. I'm just going down the next question down the line here. One question is, how often do you see these analyses including additional items of current discharging into the earth in the model that will cause the Earth's surface potential to rise at these locations? Items such as connected transmission lines, pipelines, towers. So essentially the question is asking, how detailed do we get with these models? Really, you want to get as detailed as you can. I know we're coming up at the top of the hour, so I won't answer this question, and I will make sure to respond to everybody's questions via email if I didn't get to them during this webinar. I appreciate everybody standing on. So if you have a question, do enter that in. I will email you to get back to you. But for these models and the detail of them, you want to model as much as you can. And actually, one of our, I debated doing another case example of a, we'll say this, interference model, where you have the transmission line running out from your station. Once this loads, we'll be able to see this illustration. You want to be as detailed as you can, because what you'll see is at every one of those towers, you're going to have a peak or increase in your ground potential rise. And you can actually see that if we go to another webinar we have done. Let me go to the EasyPower.com webpage. This is a good place if you want to learn more about grounding in general, AC interference. Go to the grounding resource page. Here, we also have a reference to all of our videos. And in the, all right, fault current split. In this webinar, I'll expand the view here. You can see each one of these peaks in this Earth surface plot. So here would be our substation. This little peak is at each one of our tower grounds. By modeling that, we can get a better understanding of the actual GPR of our station, as well as the voltage out at these other systems. So more detail is generally better. Things that are far away from your recipient object, you don't need to model in detail, meaning far away, 3 to 6 times the dimension of them. Things that are close to them, you do need to model in higher detail. So here would be a nice illustration of if you have a transmission line coming out from a substation, that fault at the substation can propagate on the shield wires out to a recipient pipeline, for instance. So that would be another valid concern. Do appreciate everybody being on this webinar. I know we're at the top of the hour and I don't want to keep everybody too late. If you have any questions, please feel free to email me at dave.lewis@bentley.com. I know there are many questions I did not get to in our webinar here. Do appreciate you putting those in. Feel free to email me afterwards or put them into the GoToWebinar questions page and we'll make sure to answer those. At the end of this webinar, we do have a survey, so please stay on, and appreciate everybody's time this morning or this afternoon. Thank you, everyone. Have a great rest of your week.